My name is Simone Stumpf. I'm from City University London, and I've done this work with my colleague Dympna, and it's based on a master's project by a student called Adrian Bussone. So what I'm going to talk about today is mainly explanations and explaining machine learning system. When I looked around the papers in this workshop, there were numerous words to describe the same thing, or possibly the same thing. There's intelligible, interpretable, transparent, understandable. I think I left out comprehensible. But, you know, there are all these kinds of words that we use to hopefully make it clear that we want to have something explained to humans to make something clearer of how machine learning works. Now, I started thinking about, well, do we actually mean the same thing by all of these words? Do we perhaps have different notions of what intelligible is and what understandable means, and how do we actually qualify that? How do we measure that, whether something is more intelligible or less intelligible, or perhaps perfectly intelligible? And what also struck me reading through the different papers was that we actually rarely measure intelligibility itself. What we actually measure is sort of a proxy, what we consider the goal of the machine learning system to be for the user. So you could measure the impact of explanations on trust, on satisfaction, on the user experience. We could also make a machine learning system more intelligible, so the user can help identify and correct mistakes, debug the machine learning system, or improve the model, help us to speed up training. And then lastly, there's also where we're just kind of going to the user, well, it just helps you with a decision, right? And hopefully by making it intelligible, it just makes sense, right? You understand how it works, and therefore, you know, it should sort of like fall into place. So those are the sort of things that we want to do, and there has been quite a lot of work in this workshop and prior to it in how and what to explain to make machine learning systems more intelligible. So, well, explain the process of machine learning is a good idea. Explaining the model is a good idea. Individual predictions or data sets or these hints is probably also a good idea. And various forms of explanations have been explored, from textual explanations like keywords to visualizations. We've seen quite a few of them. Now, all of that seems like a good idea. Right? Now, just a reminder, how machine learning systems work is not how humans work. Right? So whenever you're explaining machine learning systems, you have to take into account the way they reason is completely alien to how the user will reason. And that's where I want to sort of start talking about harmful explanations. So there has been quite a bit of work done already in automated systems. Some of them are based on machine learning, on misuse and disuse. So misuse is actually when you follow incorrect predictions or suggestions, and disuse is when you don't follow correct suggestions. So you know, it's sort of kind of going along with something when you shouldn't, and not following something when you should. And this kind of over-reliance, i.e. misuse, has actually been very well documented for automated systems. So people go along with stuff that they shouldn't. So we're trying to explore that a little bit more, and directly in relation to explanations. So this reports a case study that was published at ICHI, which is the International Conference on Health Informatics. And what we did a Wizard of Oz study using a clinical decision support system that diagnoses balance disorders. And you can see it in the sort of bottom right corner. It allows a healthcare professional to actually stick in data, medical history, symptoms, and then it comes back with a diagnosis and then eventually also a treatment plan. And what we did is we gave 7 healthcare professionals 8 hypothetical cases, so 8 patients with various symptoms and backgrounds, and then they entered that into the system, and then they were presented with a diagnosis from the system. So very small scale study, because in that sort of domain, it's really, really difficult to get these healthcare professionals to actually participate in any of these experiments. They were family practitioners, primary care physicians, so their average consultation with a patient takes 10 minutes. So, prizing them away for half an hour or even an hour is incredibly difficult. So we would like to extend that sample, but for the purposes of this, we weren't able to. So what we tweaked in this little study was that we gave them a diagnosis based on the data, the cases, and sometimes they were wrong, and sometimes they were right, so i.e. sometimes they should follow or agree with the diagnosis, and sometimes they shouldn't because it's wrong. We also gave a certainty figure, which we adapted, so some of them had high confidence and some of them had low confidence. And then we tweaked the explanations. So we borrowed an idea from Todd, which was the soundness versus completeness, and we actually gave them more matches, more explanations of why this diagnosis was correct versus fewer. So one is the more comprehensive explanation, and one of them is the more selective explanation. Correct versus incorrect, we sort of balanced it in the 8 cases, 4 were correct, 4 were incorrect, and so on. So it was completely fictitious. We didn't actually train a model. We didn't need to. So let's just quickly look over the results. What we seem to find is that with the comprehensive explanations, they definitely seem to affect trust. So the graph on the left, the blue ones are the ones that had the more comprehensive explanations, whereas the green ones had the selective explanations. And as you can see, we measured it before they actually interacted with the clinical decision support system, and then afterwards, and the trust always went up with more comprehensive explanations, whereas they stayed fairly static with the selective explanations. The diagram on the right probably takes a little bit of explanation. So you can see on the left column you have the comprehensive explanations, on the right column the selective explanations. The ticks are where they agreed with the with the diagnosis. The crosses are where they disagreed with the diagnosis. And the red ones are when they shouldn't have. So that was a wrong agreement. Right? So what it appears, and again, there's no statistics behind this, and it would be really, really interesting to ramp this up, is that it seems that with fewer explanations, so with more selective explanations, people rely more on themselves. But that was actually quite dangerous because they were relying more on themselves when they shouldn't have. They actually disagreed with a correct diagnosis. On the other hand, with comprehensive explanations, what seems to happen is that they actually seem to agree more with incorrect with incorrect diagnosis. So they went along with predictions, with diagnosis, when they should have said, no, that's not right. So it seems then that more explanation leads to more over-reliance, and fewer explanations, or less explanation, leads to more self-reliance. We realized that we didn't show them everything that we could have possibly shown, so we also asked, well, what else would have been helpful to actually give you more confidence that you're making the right decision. We showed certainty, and they were really interested in that, but they didn't understand what it actually was, how it was derived, and so they wanted to know, well, how sure are you that this diagnosis is correct? But also they wanted really deep understanding of how that was derived. They also wanted more evidence for and against, and that actually goes along with a particular way that physicians, clinicians, doctors make decisions. They use a differential diagnosis. So what they actually have is two competing diagnoses in mind and trying to sort of race them off against each other. Right? So they're trying to find counter-evidence for one and the other at the same time to sort of say, okay, which one is it actually? And what was also quite interesting, which is again how physicians are trained, how they make decisions, which is not like machine learning systems currently reason is. Well, they were really wondering, well, how does this case present? Is that actually a typical presentation of this case? Is it an 80-year-old woman who keeps falling down constantly, right? Or is it somebody who's 35 who has sort of balance issues? So they were interested in typical presentation as well. So, in conclusion, they are actually trained quite a lot to reason in a certain way, which the machine learning system kind of ignores. And it's definitely not explaining itself in a way that a physician or a clinician would reason and understand and find intelligible. What we also seem to have found is that, well, these explanations are actually not that great. They are harmful because what seems to be happening is that explanations are like rhetorical argument structures. So if you're familiar with rhetoric, I persuade you. So if I give you more explanation, if I give you more evidence, you are going to go along with it because I persuade you. The persuasive force is greater. And so explanations in machine learning systems seem to be almost acting like those, so they can actually have harmful effects. Which then leads me on to sort of the bigger question, well, if we know that explanations are not universally good, how do we actually develop appropriate explanations? So are there explanations that can be better in some circumstances but not in others? Should I use certain explanation at a certain point but not in others? To then sort of shape the trust or the decision of the user appropriately. Okay.